Okay, here we go. Let's have a look. So,
I don't wait. We're sketching this.
yeah, that's an
I
easy
just found
sketch,
the
right?
answer.
What's
Different answers.
so let's.
Is this what the sketch should be?
You never taught us
Three?
sketches.
Oh,
Was that just
I don't need
basic
to.
bio
That's
reader?
not anything you need to be taught.
Oh,
So what's this look like? What's the curve look like?
It's a straight line at 3.
It's a line.
Straight line at 3, and right, we're looking at the area underneath that curve from 0 to 5. So 1, 2, 3, 4, 5. So from there, that's A, and that's B, right? And so this is the area in question, right?
3 times 5
Okay.
minus
Yes.
So let's set that up as a definite integral. How would I write that as a definite integral? The integral of,
0 to 5.
okay, so the integral from 0 to 5 of,
3x.
that's it.
Wait, what about the answer?
The what?
Never mind.
Oh, you mean the actual, okay, if we do the calculus is what you're saying, right? So we could answer this, okay, stop talking. Okay, so we could answer this using calculus, or in this case, maybe we can find an easier way. Let's do the calculus real quick. What's the antiderivative of 3?
3x.
3x. Okay, now I want to show this will help us a little bit too. So we're going to get 3x evaluated from 0 to 5, right? Okay, but we could think what that's going to amount to. That's going to amount to 3 times 5 minus 3 times 0, right? No big deal. So in this case, that's really easy to just plug those in. But in the future, maybe we'll have bigger antiderivatives here that we have to evaluate, right? So the same kinds of things apply that would normally apply with algebra, where we're taking a difference of two terms. So I can factor out like factors. In other words, I could pull this 3 outside of the brackets. Everybody see that? So I could just do this. I could rewrite this as 3 times x evaluated from 0 to 5. You see the difference? Well, okay, it's not. In this case, it's not. In this case, if we were to use this technique here, we're just going to get 3 times 5 minus 3 times 0, right? But if we use this technique, we get 3 times 5 minus 0. No difference here at all. But in some cases, there may be a difference, right? Well, I mean, in terms of just the difficulty of evaluating the expressions, right? Sometimes it's helpful to factor something out because it makes the number smaller, right? Either way, we get 15, don't we? Okay, did we even need to do the integral though? No. Because an integral represents an area under a curve, and that's not a calculus type curve. That's a regular old geometry type curve, right? Well, in this case, we wouldn't have even, I mean, we could sketch it, or we could just even do it in our head. We could just think, okay, well, this is a function with a height of 3 that's constant and a width of 5, so the area is 15, right? Because it's just 3 times 5, right?
Wait, the area equals, I thought that was what C equals.
No, that's the area. Remember now, let's refresh just a little bit here. So if I give you a problem that looks similar to this, but is actually completely different, if I were to have said, what's the antiderivative of, or the indefinite integral we would call it, okay, of 3 dx, you would have told me 3x plus c, right? Okay, that's what we call an indefinite integral because it's got that c attached to it, right? See what I'm saying? It's indefinite. We can only answer that to within a constant. And the answer to an indefinite integral is always going to be a family of curves, right? It's going to give us back a function. It's telling us the family of curves whose derivatives are 3, right? Yes, ma'am.
So like in the book we have like the parabola and black and other parabola gray, is that what?
Yes, it is, exactly. So in the book, what that's showing you then is, it's saying, okay, so there's an infinite, like in this case, our answer would just be all lines with a slope of 3, right? That's what it is. So we're going to get a whole bunch of lines with a slope of 3. What's the c stand for? Plus c. Well, that's just the y-intercept, right? So we're going to, now if we had some initial condition, we were solving a differential equation, then maybe we'd say something like, okay, well, we want the one that's gonna give us an answer of 4 when x equals, or of 6 when x equals 1, right? So in that case, we would have to have c equals 3, right?
Right.
And so we would choose the one trajectory with a y-intercept of 3, right? Does that make sense? Okay. But a definite integral is an area under a curve, and so the answer is a number. That's it. We're gonna get back a number. We're looking for the value. What is the area under that curve?
15.
Right? And it's 15. Yeah. Okay.
So,
Okay. Question.
that equation will always give the area too.
Yes.
Okay.
Yeah. It's bizarre that it does that. It doesn't. Why would it? It doesn't seem like it should. And if we have time at the end of the year, we'll kind of reflect back on this and say, okay, now,
Just the end of the year.
I know.
Take it in.
I mean, the very end of the year.
It is the very
Yeah, we're getting close.
We almost got him.
So, I mean, I'm just saying, if we've been able to take a day and just kind of look at this and say, okay, well, why did it do that? You know, because you can sort of get a feel for why it did. I could draw some pictures that would represent it. But honestly, for now, the most important thing is just that you know that's the trick, right? This is what we call the fundamental theorem of calculus, right? This is the one that just tells us that the area under a curve is given to us by that trick.
Didn't we
Love that trick.
prove that yesterday?
Can you leave that up there? I wasn't here. I'm gonna write that down.
Yeah.
Okay?
Why did I write that? We got it.
Make sure you write down the orange part too.
Oh, that's true.
Uh-huh.
So capital F is the antiderivative
Oh,
of,
I thought it was.
okay? Yep.
Is that pretty standard then, that you, like, capital F is antiderivative?
Yes. Yep. That's pretty standard.
So, when are we gonna take a test over this?
Soon.
Wait, we're having the test.
Yeah. Oh, yeah.
Okay, is it gonna be just like this, like easy?
Yeah, it's not gonna be hard.
Okay.
Yeah. I just want you to know how to do this stuff. Okay, so let's look at some other properties of this. Well, you're gonna have to, I'll put the video up, Ron. You can look at that. Okay, so let's look at another one. How about this one? What is going to be,
4. It'll be 4.
Yeah.
Is that after what you're saying?
Mhm.
I think so. I know Ellie Lynch.
how about that one? So I wanna find the area under the curve 4 minus the absolute value of x from -4 to 4. Okay, so that looks nasty already, right? Because we got an absolute value function.
Yeah.
If we want to do this analytically, we've got to rewrite the absolute value function as a piecewise function, yada, yada, yada. Do we really want to do that?
No.
Okay, is there an easier way?
Yes.
Yeah, there is. This is an easy area, right?
Yes.
What does 4 minus the absolute value of x look like? Well, what's an absolute value of x look like? It's just a b, right? Okay. So isn't this just going to look like then, if I were to graph this? Yeah, all it's gonna be is, instead of being just a regular old b, if we subtract that from 4, it's the same thing as multiplying it by -1, which means that we're gonna flip it and add 4 to it, right? So it's just gonna look like this. Right? It's just gonna be so that's 4, and that's 4, and that's 4. Easy. What's the area?
4.
Yeah, half base times the height, which is 16, right? Yep. Okay. So the answer is 16. Moral of the story, that was way easier to just sketch what that thing looks like, and it's got a straight top on it, right? So you don't need any fancy calculus, because it's not curvy. So we can just add it up, right? Okay, so how about one more?
Will you actually write that down? I'm sorry. Yeah, how do you get 16?
How did I get 16? Okay, because all we did, 4 minus let's do this in a couple
Half
steps.
base times height is
How do we
-4.
know?
Okay, so the absolute value of x, absolute value of x is just an upward opening v, right, with slopes of 1 and -1.
Yes.
So -1 times that, you bet, is gonna flip it around, right?
Right.
So it's gonna be a downward opening V with slopes of 1 and -1, right? So if we pick that thing up, it really just goes forever, doesn't it? If we add 4 to that, we're just vertically offsetting it by 4, and so all these points are just getting moved up by 4, and so we just get the blue triangle,
Why do we have 4?
because it tells us to,
Oh, the 4 times 4 times the 5.
right? Because 4 minus the absolute value of x is the same thing as -1 times the absolute value of x plus 4.
The only thing I don't understand is like, why did we stop the triangle up there?
Oh, we didn't. It goes forever.
So how does that make the area 16 then? I understand.
Because
how
we're going from -4 to 4. Oh,
Can
right.
you write it out? I'm sorry. Like what you did.
Yeah, I understand that.
Sure, to get 16. So all I did to get 16
I forgot about that.
was just add up the area of this triangle. 1/2 the base times height. So the base is 8, because that's going from -4 up to 4, right? And so the base is 8 and the height is 4. So all we did was just find the area of a triangle with a base of 4 and a base of 8 and a height of 4. Okay?
Okay.
Okay?
Okay.
So what about this one? What if I did the square root of
And you're gonna make that stupid.
Is this a new example?
yeah, square root of
Turn really
4 minus x squared from -2 to 2. Okay, that looks horrible, but once again, what is that function? What is the square root of 4 minus x squared? That's the square root of 2 squared minus 4 squared. Does that look familiar?
2 squared minus 4 squared?
Isn't that just the?
No, what is that?
Isn't that like a
Is it square?
How did you square it?
Absolute value.
What's this?
2 minus x?
Triangle.
That's okay. That's the formula for
Radius.
that's the formula for a circle, right? You guys talk about that last time? You did? Okay.
Yes, we did.
You did? Okay.
Like barely.
So in this case, we've just got x squared plus y squared equals 2 squared, right? So the radius is 2. So all this is this is just graphing a circle of radius 2, right? If we solve for y, we're going to get y equals plus or minus the square root of r squared minus x squared, right? And you don't have to know this stuff. It's not like you're going to be tested on this. I just want you to see here that once again, this is just the one that we don't have to do the complicated calculus on. If we recognize that this is just a semicircle. You may not recognize that now. I mean, if you don't, maybe I photoshopped it a little bit. That might have been, but you will in college, because you'll do, as a part of your analysis and or calculus in college, you're going to do analytic geometry. You're going to spend a little time dealing with stuff like this, where you're dealing with circles, ellipses, hyperbole, and parabolas, right? And you're going to look at how you can, you just haven't done very much of that, I don't think. You remember, have you dealt with things like focus and directrix and things like that? Okay, never mind. Forget that last question. But if you did recognize it, if you recognize that this was a semicircle with radius 2 centered on the origin, then all you would have to do, this is a pretty easy one to draw. And once again, my point is just that,
I thought we just drew it. You don't always have to.
well,
That
that's
was for the other.
the whole circle. This is just the top semicircle.
Right.
And so this is just half of the area of a circle with radius 2.
Right at the bottom, would it be like negative square root of 4 minus x squared, or how would you know it was the bottom?
Say it again.
How would you know that it was the bottom half of the
I'd know, well, because it doesn't have I know it's the top half because it doesn't have a negative sign.
So that's.
Yeah, that's how you know. Yeah. Yeah, because y is plus or minus, right? The plus is the top half, the y is the minus is the bottom half. But you'll deal with that later. But anyway, that'd be an easy thing to solve too, wouldn't it? Right? No big deal. Right? I'm just gonna get 1/2 of pi times 2 squared. So what is that? 2 pi? My answer.
Yeah.
Okay. All right. So let's look at. I want you to see something else here. Let's. Okay. Let's do this. Let's get a little practice here, a little legitimate practice. Let's do easy practice. You got it, easy practice.
That's weird to think about that, but.
Okay, how about that one?
Bless you.
Let's do this one analytically, then we'll look at how we could have done it the other way.
So x squared over 2,
So you're gonna get x squared over 2, okay,
which means we're gonna get
evaluated from negative 2 to 2, okay? So if I want to, I could pull the 1/2 out, right? Don't have to, but I could.
You should, let's do it.
In this case, it doesn't really matter because I'm taking powers of 2 on the top anyway, but I could, right? So what is 2 squared over 2 gonna be? 2
0.
minus what's negative 2 squared
Zero.
over 2? 0. Yeah, the area is 0. How come? You tell me, let's graph this.
That's what you know.
It goes below the y-axis. Yeah.
Okay, we're only adding up the area under the curve from negative 2 to 2, right? So the area under the curve is always defined as the area between the curve and the x-axis, right? So I'm going to have some area here, and I'm going to have some area here. Yeah, why do you suppose it cancels?
It's reciprocals.
Okay, there must be something going on here. What if I were to do,
It's magic.
any suggestions? Okay, kind of. Let's look at just the red part for a second. Let's calculate the area under the curve x dx from negative 2 to 0. Right? See what we get. Yeah, so we're going to end up getting x squared over 2 evaluated from negative 2 to 0, right? So that means I'm going to get 0 squared over 2, which is 0, minus negative 2 squared over 2, which is 2. How about that? It's a negative area. Why do you suppose it's negative? How come, Alex? Just below the x-axis. Okay, so you can't geometrically have negative area, but in calculus, you can. Because an area, now it's not real area. This is different. This is an area, listen please, this is an area under a curve, right? And so this area, think about what this area is meaning. This isn't like, it's not like we're calculating the surface area of a shape or something, right? It's different. What we're calculating is the area in whatever the space of this plane is, right? So for example, let's look at this from a calculus or from a physics perspective for a second. What if we were going to do, let's say we were going to calculate some work, okay? We were going to look at the area under a force distance curve, okay? So let's look at the work done by gravity when an object is being thrown up into the air, so on its way up, right? So what's going on there? Well, we've got, we're going to add up the area under the curve, F times D times cosine theta, right? So what we're going to think of as our F here is really going to be F times cosine theta. We're going to think of the component of the force in the direction of, in the vertical direction, right? Okay, so when we do that, when the object is traveling upward, right, gravity's pushing it downward. Does that make sense? So really the force then, we could think of that force as being a negative thing because it's tending to slow the object down. It's opposite of the displacement, right? So it's going to look like this then. It's just going to look something like that. Okay. As the object moves along upward, the force acting on it is negative, and so the area under the curve is negative, which it needs to be, doesn't it? Right? Because we know that, from physics, we know that if the displacement and the force vectors are in opposite directions, that means negative work, right? So it's important for us, long story short, it's important for us in calculus to be able to define something like negative area, because a lot of times the quantities we calculate using areas under curves need to be negative, right? Okay? So it serves a purpose. So we just learned something about area. First important lesson about area. Area is reckoned to be positive when it's above the x-axis and negative when it's below the x-axis, or whatever the axis of the independent variable is. A lot of times in physics, we don't use x, we use t. That's all right. Doesn't matter.
Wait, so that means that the one with the absolute value with the negative work could have been like this one, where it would have been zero?
It,
Wasn't
well,
the absolute value?
I mean, without the absolute value, it would have been, yeah. Yep. Okay, so let's look at another one here. That's one lesson learned, right? Area under a curve is positive when it's above the x-axis, negative when it's below the x-axis. Okay, good. Let's try another one. Let's calculate this. Let's find what is the area under the function x squared from 0 to 1. Okay, so we can do this one, no big deal. What's the antiderivative of x squared? And we're just going to evaluate that from 0 to 1. Having 0 on the bottom of as the lower limit of integration makes things easy, doesn't it?
Yeah.
Because, I mean, it's just, unless you're dealing with a trig function or something like that, it's 0, right? You're going to get back 0. So, well, I shouldn't always say that. I mean, it's usually going to be 0. There will be cases where it won't. You'll see some. But what's my answer? 1/3. Okay, good. So let's add up the area under the curve x squared dx, starting at 1 and ending at 0. So that's going to give us 0 minus 1/3 equals negative 1/3. Well, that's weird. What's the only thing I did different there?
Change the
I flipped the limits of integration. So I changed the direction in which I swept out area. So we'd also say this. We reckon area as being positive when we sweep it out from left to right and the area is above the x-axis, right? If we sweep it from right to left, it's going to be the opposite sign. Okay?
Wait, so if you cross the x-axis going the other way, then it's positive?
Yes. So if it were, that's right. So it'd be like a double negative, wouldn't it? If it were below the x-axis and we swept it out backwards, it would make it positive. Yeah, that's true. Two negatives make a positive. There you go. Oh, sometimes calculus will do it. Okay, so how about this?
Hey.
Can you simplify that expression for area?
Yes.
You can.
Let's do it general.
There's something going on there.
Oh my god.
Yeah, what's going on? Okay, good. Good. Okay, you see why? Very good. Because think what this is saying. This is saying that we're going to add up the area under the curve F from A to B, get an answer, and then we're going to add up the area under the curve F from B to C and get an answer. But because the upper limit of the first integral is B, so the ending point of the first area is B, and the starting point of the second area is B, why do we need the B? We'll just go from A to C, right? Okay? And because we now know that adding up area backwards makes it negative, it even works if B is greater than C, right? I mean, think about this one. So what if we have the area under the curve x dx from 0 to 5 plus the area under the curve x dx from 5 to 2? Well,
So-
then I'm going to get a positive area here, right? And then I'm adding from 5 backwards to 2, so that makes it negative. And so it works. I'm just going to be subtracting away the extra area then, right? And what's my final answer going to be? Yeah,
So
0
you're
to
not
2.
taking the displacement, you're just taking the total position.
Right.
No,
we're
I
just-
mean, you're just taking displacement. You're not taking the total actual way it sweeps out.
Well,
Because that would be more area. If
so,
you were to-
so what this, yeah, so what it looks like is this then. We could draw this one. So if this is 2, 3, 4, 5. Okay, so we did this in 2 parts. Here's the blue part, right? So the blue part was we added up the area under the curve x from 0 to 2, right? Actually, from 0 to 5. So clear out to there, right? Now that's positive area, right? So that's the blue integral. The red integral is going to have us start here and go backwards to 2. Because we're going backwards, that's going to be a negative area, right? Does that make sense? So we got the big blue area plus the fairly big negative red area gives us the small positive purple area. See? Okay. And so I think what's interesting and what's cool about that is that the areas, it all works out. It works out so you don't even have to worry about B being in the middle. A, B, and C could be any place. It doesn't matter what the order is. This will always be true, right? Okay. A could be bigger than C for that matter, right? Okay. All right, so what else? Oh, I got one. How about this one? I'm gonna challenge you guys a little bit on this one. Let's try. Oh.
Zero.
What is it?
Zero.
How come, Brady?
I was like, they're not moving anywhere.
Ah, okay. Braden saw it. They're the same. There's no width to this interval. It doesn't matter how ridiculously hard I made the function, it's got no width, and so the area is 0. Okay. Trick question. Exactly.
Can you throw something like that on the test?
Sure. I'll throw you one like that on the test. You gotta recognize it.
Maybe 48 points.
Yeah, that's not very
Stick your
nice.
paint on that. No, no trick, but like. Yeah.
Yeah, if it's gonna be trick, have it be like this problem.
Okay.
You want to drink?
5,000.
Yeah.
Okay, I think we're pretty good with all that. Oh. Alright, let's try. Okay, try this one, please. Oh.
I just threw breaks.
I remember keeping the journal of how many days we were on.
Okay, try that.
Fifth grade. That was good.
Somebody lose a Bobby pin? I don't think this is mine.
Oh, sorry.
Right there if you need.
Take it down, please.
constants?
or whatever there are, numbers.
You,
Wait, you're saying like factor out?
I do too.
What concept?
Wait, could you factor out?
Oh,
X?
you can make them.
You can't factor out next.
But I don't like one half
But
and one
can you
third.
make them common denominators and then factor out?
No, a constant you could.
Yeah, but if you made them common denominators.
Okay, but first thing you want to remember here is that if I'm dealing with an antiderivative, that's all we're working with right now, is an antiderivative, right?
Yeah.
The antiderivative of a sum of terms, we just deal with it term by term, right?
Yeah.
So we're gonna get an answer from the first term,
Yeah.
which is what?
X squared.
X squared over two.
Okay, and I think I know what you're asking now. And the second one is gonna be minus,
X
cubed over three.
okay, good, and so now we've got choices, right?
Yeah.
Now we got a bunch of choices. There's a bunch of different ways we can evaluate this. There's no right or wrong answer. But I do want you to see that there are differences that someday you might want to exploit, right? So one way would be to say, we could then write this as the quantity, x squared over 2 minus x cubed over 3 evaluated from 0 to 1. That's fine. So that means, what I mean by that is, I'm going to plug 1 into the whole ball of wax, get an answer, and then subtract from that everything evaluated at 0, right?
So what's our answer? What's
Well,
X?
we'll get an answer. Okay. So if we do it that way, we're just going to get 1/2 minus 1/3
Negative
minus 0.
So
So what's this?
Yeah.
Okay, another way we can do it. We'll call this the purple way. So the purple way would be to break these up into separate parts. So I'm going to get x over 2, x squared over 2, evaluated from 0 to 1, minus x cubed over 3, evaluated from 0 to 1. Okay, that's going to give us something, same answer, right? But you see the difference. That's going to be the same thing as saying 1/2 minus 0 minus 1/3 minus 0. Same thing, right? Question?
So, well, just the way I was like asking her, could you make just that, make it 3 squared over 6 minus 2, 3x squared over 6 minus 2x cubed over 6?
You could. I think that's.
Just take out the 1/6.
You could, but I think you're making it harder.
Okay.
Because wouldn't you rather? And here's why I say that, Riley. Because wouldn't it be easier to combine the fractions once we've gotten rid of the variables by evaluation? You see what I'm saying? Yeah. So generally this is going to make things. These are oftentimes definite integrals. We're going to find are easier to do than indefinite integrals, and we won't really be able to appreciate that for a while, but eventually we will. But I think when we're at the very end of what we cover, you'll kind of see why these kinds are oftentimes better, easier to work with. Okay, well, for one thing they are because you can do them on your calculator. Yeah,
But you're not gonna tell
you
us
can
that.
do definite integrals on your calculator. You can't do indefinite integrals unless you have TI-9 or with TI Inspire. You know, the CAS version, but you can do definite integrals on a calculator. I'll show you how tomorrow. The rest of this week, I'll give you one work day. Yeah. I'll give you one work day.